for me, this has been a wonderful conference because this is one of the first times or few times that I've actually been able to engage in a plethora of ideas relative to climate change. I was able to actually listen to what the folks were saying about the greenhouse gas theory, and they actually were able to listen to the research that my colleague, Dr. Nikolov, and I have been able to do that actually brings some new information into the climate scenario.
So what kind of new information are we talking about here, Dr. Nikolov?
Well, the new information relates to our discovery of a relationship across planets that we have found based on NASA data, updated NASA data. And this relationship reveals a new understanding or a new nature about the greenhouse effect, and that is that the greenhouse effect or the thermal effect of the atmosphere is caused by atmospheric pressure, and it's independent of atmospheric composition. For the first time, at least to my knowledge, since the greenhouse theory has been proposed some 190 years ago, for the first time we've been able to test the hypothesis that the Earth is a part of a continuum in terms of climate, and that the same laws that govern the climates of other planets will also govern the climate of Earth. And we, through our analysis, were able to see, to show, to discover what those main drivers are.
So the universality of the applicability of a law broadens its scope and increases its validity. Is that not right, Dr. Zeller?
And the amazing thing is that you would think that or we all think, our belief before we had this discovery was that the Earth was in fact a special case because we have water vapor, we have things that the other planets do not have. Lo and behold, by using NASA data, actual measured probes that NASA has made through the years, through the last 30 years, we've been able to put together a unified theory of how the atmosphere truly works. Believe it or not, we can predict the temperature of the Earth, the long-term temperature, global average, within less than a degree by using the data from other rocky surface planets, like Venus, Mars, Triton, and Titan.
Well, this is amazing because that range of bodies spans an amazing range of temperatures, atmospheric pressures,
it does.
And distances from the sun.
Composition.
It does.
And atmospheric composition. Yeah. So how and so does this mean that composition is less important than the mass of the atmosphere?
Yes. So our results have nothing to do. Actually, it shows the pressure, and as Dr. Nikolov was saying, the amount of sun that each individual celestial body gets. One of the amazing things here recently, our paper was published last April or so, we predicted what the temperature of Pluto would be. And it was right on. It was amazing.
Based on the available data right now.
Because that data's only just arrived from NASA, hasn't it? The more accurate data on Pluto has only arrived within the last 12 months.
Yeah.
But you'd already made a prediction in advance of that.
Pluto's a rocky surface planet with a thin atmosphere.
And which other planets do you now have predictions for, which NASA will be visiting in the near future?
Well, we have
Jupiter and Callisto, which are satellites.
Callisto. Jupiter's Callisto. Yeah.
Jupiter and Callisto are, and also Mercury.
Europa and Callisto.
I'm sorry, Europa and Callisto, the two moons of Jupiter, and I was thinking about the moon, the main planet, but they're the two moons of Jupiter, and Mercury, which is the smallest planet close to the sun.
We don't have that data yet, but it turns out that the NASA prediction for Mercury is something like 150, 140 degrees.
But is that an average surface temperature that you've been able to work out from an equator to pole difference, or how do you go about that kind of dealing with those kind of gradients?
The published information that we have in the paper refers to the global average temperature, but we do have calculations for the temperature difference between the poles and the equator on those bodies, which it will come out in the next paper, but right now.
Okay, so that's another way in which your hypothesis, your
Yeah.
theoretical work could be validated, is not only in the overall average surface temperature, but in the equator to pole gradient and the
gradient as
differences.
well.
Yeah.
Yeah.
But what's been fascinating about this particular conference is the amazing interest in the interchange between the scientists who have reported on the current greenhouse gas theory. They're very familiar with it. They know it. But we find that they were actually interested in some of our work that in some cases, well, it goes contrary to some of the papers that were given at this conference.
So the scientific ethos and method is alive still. That's good to hear.
It is still alive. It was wonderful.
Yeah, I was surprised
Breath
to
of fresh
see.
air.
I was surprised to see the same thing, that the reception among, especially younger participants of the conference that have been educated in the current theory, and that's pretty much the only thing that they knew, that they were curious about our findings, and actually they found it insightful and something to think about. So.
Excellent.
That's
Well, this
encouraging.
augurs well for the future of science, and thank you, gentlemen, for your time this evening.
There was one young student, for a particular, who had given a paper on the radiative transfer theory and how it worked, and how he was looking at the carbon dioxide absorption, and at the coffee break we talked to him at length, and his professor was there, about how my goodness, some of these models are not simultaneously considering the convection and the radiative transfer, and we left that discussion with actually from some new opportunities for modeling that they had not seen before. And for us, we don't do that kind of modeling, so for us it's exciting. Yeah.
I agree. Yeah.
Fantastic.
Yeah.
Well, terrific. Let's look forward to future progress and future papers from you guys, and thanks very much for your time today.
Thank you.